Hey everyone, and welcome. Today we're diving into a Leetcode problem called Longest Unequal Adjacent Group Subsequence 2. It sounds like a bit of a mouthful, but don't worry, we'll break it down step by step and figure out a smart way to solve it. Ready? Let's go. So here's the deal. We're given a list of words, and for each word we also get a group number from a second list called. Our main goal is to pick out a sequence of these words. Actually, it's a subsequence, which means they have to stay in their original relative order, but we can skip some. We want this subsequence to be as long as absolutely possible. But of course, there are some specific rules for which words can be neighbors in our chosen subsequence. Okay, let's talk about those rules. If we pick two words to be right next to each other in our special subsequence, let's imagine one word is word A, and the next is word B. First, their group numbers from that list must be different. So if word A is in group 1, word B can't also be in group 1. Second, word A and word B must have the exact same number of letters. Their lengths have to match. And third, they need to be almost identical. Only one single letter should be different between word A and word B. This is what we call a Hamming distance of 1. All three of these conditions must be true for two words to be adjacent in our subsequence. Let's make this concrete with an example. Suppose our list of words is and their group numbers from the list are 1, 2, and then 2 again, respectively. So this means is in group 1, is in group 2, and is also in group 2. Okay, let's try to build a subsequence. Can the word be followed by fix? First, let's check their groups. Wesley is in group 1 and is in group 2. Are 1 and 2 different? Yes, they are. So, rule 1 is satisfied. Next, their lengths. Can a word by fix, for a year free, has 3 letters? Also has 3 letters. Are they the same length? Yes. Rule 2. Check. Finally, the Hamming distance. How different are and the J? Let's see, compared to the second and third letters and are the same. Only the first letters and are different. So they differ in just one position. That's a Hamming distance of 1. Rule 3. Check. Since all rules passed, we could have the subsequence. Then, that's a length of 2. What about followed by is group 1? Is group 2? Different groups? Yep. Same length? And both have 3 letters? Yep. Hamming distance 1. Versus just the first letter is different again. So, yes. Santi Raya Pigoling Manjix then is also a valid sequence of length 2. Now, what if we tried followed by Daring Gamelang is in group 2? Daring is also in group 2. Are the groups different? No, they're both group 2. So this pair fails. The first rule cannot be followed by in our subsequence. It looks like the longest subsequence we can get in this example has a length of 2. For instance, then, this problem has that classic longest subsequence flavor, doesn't it? And whenever you hear longest subsequence or shortest path or something similar, it's often a good hint that dynamic programming, or DP for short, might be a great approach. The main idea with dynamic programming is to build up the solution by looking at smaller, manageable pieces or subproblems. And, crucially, we remember the answers to these smaller pieces so we don't have to recalculate them over and over again. So, for our dynamic programming approach, we need to define what information we're going to keep track of. We'll use an array. Let's call it our DP array. For every word in our input list, say the word at position the value dp at I, we'll store the length of the longest valid subsequence we can form that ends with that specific word. To help us actually reconstruct the sequence of words later, not just its length, we'll use another array. Let's call this one the previous index array. So Jax, previous index at I will store the position, or index, of the word that came just before the word in the best subsequence ending at. How do we start? Well, any single word, all by itself, can be considered a valid subsequence of length 1. Right? So we'll initialize all the values in our DP array to 1. Each DP at I will be 1 to begin with. Now the core idea. To figure out the true DP value for a word at a particular position, we need to look back at all the words that appeared before it in the original list. Let's say we're looking at a previous word at position, where is less than. For each of these preceding words, the one at position, we ask a critical question. Can this word legally come right before our current word? This means, Do these two words, the word and the word, satisfy all three of our rules? You know, different groups, same length, and a Hamming distance of exactly 1. If they do satisfy all the rules, it means we could potentially extend the longest subsequence that ended at the word by now adding the word to it. If we do that, the new subsequence length would be whatever dp at j was, plus 1, for the word itself. Since we want the longest subsequence ending at, we'll consider all such valid. If dp at j plus 1 gives us a length that's greater than the current dp at I, we update dp at I to this new longer length. Just a quick side note. We'll need a little helper function to calculate that Hamming distance we talked about. This function will take two words which we'll assume are the same length because our main logic will check that first. It then simply compares them letter by letter and counts up how many positions have different characters. It's pretty straightforward, but essential for our rule checks. Alright, here's the Python code that pulls all these dynamic programming ideas together. I know, code blocks can sometimes look a bit dense at first glance, but no worries at all. We're going to walk through the important parts one by one, explaining what each bit does in plain English, nice and easy. Okay, first things first. If there are no words in the input, which means the number of words is 0, we just return an empty list. Simple. Otherwise, we set up our dp array and our previous index array. As we discussed, every element in the dp array starts at 1, because any single word is a valid subsequence of length 1. All elements in the previous index array start at -1, signifying that, initially, these length 1 subsequences don't have a predecessor. We also initialize a variable max length to 1 and end index to 0. This means, at the very start, we assume the longest subsequence we've found is just the first word itself. These will get updated as we find longer subsequences. Next, we have the heart of our DP solution, the nested loops. The outer loop, using the variable, iterates through each word in our input list, from the first word up to the last. For each of these words, its DP value is already 1, and its previous index is -1. The inner loop, using the variable, then iterates through all the words that came before the current word, so it goes from 0 up to -1. The purpose of this inner loop is to find if any of these words can act as a valid predecessor to our current word. Inside that inner loop, for each pair of an word and a preceding word, this is where we meticulously check our three crucial rules. First, are their group numbers different? That is the group of the word not equal to the group of the word? Second, do they have the same length? Is the length of the word equal to the length of the word? Only if both of these are true, do we then proceed to the third check. Is the Hamming distance between the word and the word exactly 1? All three of these conditions must hold true for the word to be a candidate to come before the word. Now, if all those three conditions are met, it means we've found a word that can indeed precede our word. This opens up the possibility of forming a longer subsequence. We can take the subsequence that ended at the word, which had a length of dp at j, and extend it by adding our current word. This new potential length would be dp at j plus 1. We then check, is this new length greater than the current best length we've found so far for a subsequence ending at, which is stored in dp at I? If it is greater, then we've found a better way to form a subsequence ending at, so we update dp at I to this new larger length. And very importantly, we record that the word is the predecessor of the word in this new best subsequence by setting previous index at I to. After the inner loop finishes for a particular word, we will have explored all possible predecessors for it. At this point, dp at I holds the length of the longest valid subsequence that ends with this word. Now we compare this length dp at I with the max length variable, which stores the longest subsequence length found anywhere in the list so far. If dp at I is greater than our current max length, it means we've just found a new, even longer overall subsequence. So we update the Forhaston Mengel van Okay, once both loops have completed, our 2p array is fully populated. Max length holds the actual length of the longest subsequence, End index tells us the position of the last word in that subsequence. Now, we need to reconstruct the actual list of words. We initialize an empty list called result sequence words. We start with a pointer set to our next end index. Then, as long as this pointer is not -1, which is our signal for no predecessor, we add the word at the index to our result sequence words list. After adding it, we move our pointer to what previous index at current tells us, effectively jumping to the word that came before it in the subsequence. We repeat this until it becomes -1. Since we added words by starting from the end and going backwards, our result sequence words list is in reverse order. So the very last step is to reverse this list, to get the words in their correct forward order. And that's our answer. So let's think about how efficient this dynamic programming approach is. For time complexity, we have an outer loop that runs times, where is the number of words. Inside it, there's an inner loop that, in the worst case, also runs about times. And inside that, we do a few checks, including calculating the Hamming distance. If being the worstance, calculating Hamming distance takes about operations. So altogether, the work done is roughly times. In big O notation, we say this is quote 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 quote. For space complexity, we're using two main arrays, the DP array and the previous index array. Both of these arrays have a size equal to the number of words. So the additional space we use is proportional to, we call this order n space complexity. Alright, to quickly recap what we've covered, the problem asked us to find the longest possible subsequence of words, where any two adjacent words in our chosen subsequence had to follow strict rules. They needed to belong to different groups, be of the same length, and differ by exactly one character. That's the Hamming distance of 1. Our solution was to use dynamic programming. The core idea was to build up an array, our DP array, where DP at I stored the length of the longest valid subsequence that ended specifically with the word. We used another array, the previous index array, to keep track of the path, allowing us to reconstruct the actual sequence of words once we found the overall longest length. It's a pretty standard and powerful pattern for these types of longest sequence problems. Hope this explanation made the problem and its solution a bit clearer and easier to understand. If you found it helpful, please do give that like button a click. Maybe consider subscribing for more Leetcode problem breakdowns like this one. And if you have any questions, or perhaps a different way to approach it, feel free to drop a comment below. I'd love to hear from you. And hey, if you're feeling extra generous, well, you know where the Boba Fund is. Keep practicing, keep coding, and I'll catch you in the next one.